Hi class, this chapter 4 is on chemical reactions. So I want to get you started in terms of how to think, what to go about it. Again, as we have done in the first 3 chapters, you will be seeing a boatload of either narrative PowerPoints, or they would lead you to a video on YouTube where I would have provided you a solution, or it would just kind of compile my thoughts together for some or several screencasts where I'm showing you how to do certain things. So first things first, chemical reaction, as you know, is something where or a process, I should say, where two components essentially react with each other and they generate two different components. So it's really a chemical change, as we discussed in chapter 1. Now, there are certain physical attributes that one can think about, which you can use to define whether a chemical reaction has really taken place or not. And some of those, what do you think would happen if there is a persistent change in color? So if you begin with a colorless solution and upon mixing of the two, it essentially generates a persistent color, you would say that a chemical reaction probably has taken place. If you see generation of heat, that's another one, generation of heat. You can also perhaps see generation of light. Generation of light. In addition, if a gas evolves, so you will see bubbling, and sometimes there's a possibility that gas would evolve and there will be some sense of smell associated with it. Smell associated. So with or without a smell, if you see bubbling, that means some kind of reaction will have taken place. Another one could be if a solid gets formed. Solid gets generated from two clear solutions. So these are some of the occurrences of certain points which, if occur, you can say that a chemical reaction would have taken place. So as you can perhaps realize that if a chemical reaction is occurring in a solution phase, so when we are using the word solution, it basically means that it's a homogeneous mixture, and so there are two components for that. One is the solute, the other is the solvent. So those are the two things, solute and solvent. In general, what you need to realize is that the solvent will be the one which is the bulk quantity. So whatever is in bulk quantity, that will be called as a solvent, bulk quantity, and whichever has the less number of moles, that will be called as the solute. So for example, if you have, let's say, you want to generate lemonade, okay? It's a summer afternoon, you're making for yourself some lemonade. So you take like a jug which can hold up to 1 liter of water, and to that you add just 1 teaspoon of salt. Then salt, which is smaller in amount, is going to be your solute, and it is solid in this particular case, and water is going to be your solvent for this case. Now, one thing is to view at this in a very qualitative sense. Another is to view it as a quantity. So we can look at the specific concentrations. Of course, you know, in our kitchen we would say, oh, my lemonade is more tangy than what I thought it would be, and so the concentration would mean that it's a high concentration. On the other hand, when you are in the lab, you obviously don't eat the chemicals, and so you will need to actually determine the concentrations, that is to say how much of the solute is being held by the solution. So in other words, how many moles of a certain compound have completely dissolved in solution. And so definition wise, we can say that molarity is moles of solute per liter of solution. Realize there is a complete screencast on this aspect, on this part, where I show you how to go around, go about the calculations as well. So please view that in addition to this narrated PowerPoint. And now that you know that we define molarity as moles of solute per liter of solution, let's use that to determine the grams of solute that will be required to prepare a 500 milliliter solution, which is supposed to be maintained at a concentration of 1.25 molar at its sodium hydroxide. So it's pretty straightforward, but you can view the solution, that's posted at that link. But essentially, you have to remember two things, and the first one is the definition of molarity. Molarity is equal to moles of solute divided by liter of solution. And the other definition that you need to remember is from chapter 3, that moles is equal to given mass divided by molar mass. If you know these two, you should be able to solve this. So I would encourage you to work on this and see if the solution that I have provided you, whether that makes sense or not. Okay, going forward, realize that if you're looking at the dilution of a particular solution, essentially we are looking at simply reducing the concentration. So in other words, we can very conveniently just say that during the dilution process, all you're doing is you're changing the concentration of the solution, and in doing so you're basically increasing the volume of the solution, you're increasing the volume of the solvent, you're decreasing the concentration. But realize that the number of moles that you have for the solute, the amount of solute that you have, that remains the same. Thinking about it from the perspective of a lemonade. If you think that your lemonade is tangy and you want to keep it drinkable, all you got to do is add more water. And in doing so, you add water, you perhaps go from 1 liter to 2 liter of lemonade. And in doing so, you probably have, changed the concentration, you have changed the volume. But the amount of salt, that remains the same. So the moles of solute, that will always remain same. And that's what I say here, that moles of solute are constant, and so the initial molarity times the initial volume should be equivalent to the final molarity times the final volume. And if some of these are given and the others are not, you can provided the other three variables are known, you can find out the